In. Welcome everyone at this WINAK lecture night. For today we have two lectures planned, one by Professor Calders and one by Professor Steven Latré. In between the lectures there will be a short break. Our first speaker for tonight is Calders. He studied mathematics at the University of Antwerp and also did his PhD here. He then went to the Eindhoven University of Technology and later to the ULB in Brussels to return to Antwerp in the end. Now, Toon does research in machine learning and data science, which is strongly related to the topic he discusses today. As usual, if you have any questions, you can type them in the chat at the end of the lecture. You can type them in Dutch if you're uncomfortable with typing in English. But it's easier for me if the question is typed in Dutch, in English. And I will then read your question out loud so everyone knows which question we're talking about. All right, let's begin.
All right, introduction, Thomas. So today is about algorithms and can algorithms discriminate. So the title of my talk is Machine Learning Bias In, Bias Out. And so this already gives something away. But before we get started, let's first define what is machine learning. So machine learning algorithms, they build a mathematical model based on training data to make predictions or decisions without being explicitly programmed to do so. So this means instead of programming explicitly the machine in order to take a decision, we're going to present it with examples, and then based on the examples, the machine will learn how these examples need to be classified. So a very well-known example is that of the Cypher10 dataset, and this is a dataset with thumbnails with small little pictures. And each of these pictures depict one of 10 classes. Here you see them. The first row are pictures that represent airplanes. Then we have automobiles, birds, cats, etc. And so now what a machine learning algorithm will do is it will take these images and the associated label, and it will try to learn a mathematical model. And this model should, when it is presented with a new example, be able to represent what it is. So we could try to explicitly program this if certain pixels have certain color intensities, or maybe we can compute a gradient in the picture, textures, trying to detect textures. But instead of that, we actually want the machine to learn based on the pixels a formula that allows it to predict one of the 10 classes. So once we have it, if new examples come, we run it through our mathematical model and we have our predictions. And so automobile, ship, and bird in this case. If you look at this specific task, and this Cypher task is a very well-known benchmarking task, so different algorithms are tested on it. If you let a human do it, then on average, a human can correctly classify 94% of the cases. So this came out of tests that were done with humans. And this is because some of the images are really hard because they have a very low resolution. And so here it's pretty clear, but you can imagine if the image contains a lot of clutter, that sometimes it's very hard to make the prediction. A human that is trained in this task, let's say that he or she can do 100 per minute. That's more than 1 per second, so that's quite a lot. If you compare this with a machine learning, the best known models have an accuracy that is vastly higher. It's behind my camera. It's 99%, and it can do thousands of images per second. So this clearly is a huge advantage over human in order to perform this task. Machine learning is also everywhere nowadays. It is used in many systems that you're using on a daily basis. Spam detection, for instance, and determining based on the content of an email, the words that occur in the email, whether it's a spam email or a legitimate email. A route planner as well, and because when we're planning a route from place A to place B, we are not interested in the traffic jams that are there at the current moment, but the traffic jams that will be there in these places at the moment that we will be there. in order to make this kind of predictions, route planners are using historical information. From this information, they learn models about the traffic on the route, and they can use it in order to plan routes. Also, search engine results. This is learning based on your past performance and the performance and the links that are clicked by other users that are using, for instance, Google. What are the best search results? And so the formula is being optimized behind it. Automatic translation, also tax fraud detection is something that Belgium is actually quite strong at. Also there, machine learning algorithms are being used. So these algorithms, and they are step-by-step procedures to find a good model. And here I will use this small example of an image recognition task to illustrate how machine learning might work. And so here you see different pictures of chihuahuas or muffins. And now the goal is to detect automatically which of the two an image is representing. So we have a lot of these examples that are given. And the first thing that we need to do in a machine learning approach is to describe them by measurable characteristics. Now, if you look at deep learning, the thing that Stephen will be talking about in the talk after me, and so there the measurable characteristics will be the intensity of the individual pixels. But here I've taken two characteristics, for instance, the color intensity and the number of round shapes that we can detect in the images. Based on these two characteristics, we can place each of the examples on this diagram, horizontally the number of round shapes, vertically the color intensity, and then the color of the box around it indicates the class. But okay, I think even with the boxes, you would probably be able to distinguish the chihuahuas from the muffins, but the computer can't. So based on these characteristics, it tries to learn a model, and for instance, this model would be a very poor model. And so we've learned a linear classifier where we just separate examples from the positive class and a negative class by a line. Things that are on the right-hand side of the line are predicted as being negative examples. Things on the left-hand side, positive examples. So this is a poor model, and so an algorithm will actually try to optimize and learn more something like this model that separates our positive examples from the negative examples. Once we have this model, we can use it to classify new examples that might come. And so here we have an image. We compute the number of round shapes and the color intensity. We look at the side of the line that it is falling. So it's on the negative side. So we predict it's not a chihuahua, it's a muffin. Voila, that's what's happening here. Many types of models exist. And so here I took a linear separator in this particular example. These models, they come with a learning procedure. So we're not blindly trying out every possible line, but we're actually trying to do it in a more guided procedure. So this is based on data model parameters are being updated. And so we're trying to optimize the accuracy, the number of correct predictions that are being made. And so we can, based on computing derivatives and do some kind of simulated annealing or hill climbing in order to find the best set of parameters. And so here in this case, our parameters were the intercept and the slope of the line, and an update could be based on a number of positive and negative examples that are being correctly classified. So that is what machine learning is doing. And so this leads to the conclusion, it gives a big promise, and because human decision makers, when they have to make sensitive decisions, they're usually susceptible to prejudice and bias. For instance, with respect to gender, I want to hire someone to do a job. Let's say I want to hire a new PhD student. Maybe I have some prejudices against one or the other gender, or I may have some racial stereotypes that might taint the decisions that I take. If I use data mining, then I could make a data set with all PhD students in Belgium in the past 10 years, take their characteristics, whether they were successful or not, the number of papers they published, and on the basis of that, I can actually score for new PhD students, and I can make my acceptance decision based on that. And then machine learning is free from bias, no longer based on gut feeling, but facts and statistics. But, however, unfortunately, that's not the whole story, because models will have millions of parameters and predictions cannot always be explained. So the line that I drew on the one of the previous slides, and that was separating the muffins from the chihuahuas, actually more looks like this. I have models with not just one button or two buttons that I can tweak in order to find the best model, but I have millions of these buttons. And sometimes when I learn models, they may actually overfit my data set, and which means that they are good for the training data that was given for me, but not necessarily for the data that is still going to come and for which I'm going to use it in future to make my predictions. And on top of that, models may unintentionally pick up and amplify bias from training data. I will illustrate this with two recent examples of bias in machine learning. And because actually when we started doing research in this area more than 10 years ago, people were saying, okay, this might be the case, but we don't believe that this is really such a big problem. But in the meantime, many examples have emerged, and I will illustrate two of them. The first one has to do with word embeddings. And so a word embedding is a representation of a word or a text as a vector of numbers. So for instance, here you have a number of words, banana, father, baby, and I represent them as in a four-dimensional space with numbers. Now you might wonder, why do I want to do that? And the reason for that is because most algorithms work with numbers. So you can see it as some kind of adapter and word2vec, and this is one having embeddings of words is like an adapter. So it make a classification of text. Is this a happy text or a sad text, positive text, negative text? I can actually run the words through my word embedding software. I will get coordinates for these words, and then I can use any technique before. For instance, a linear classifier, and because now I'm working with numbers, that's much easier than working with words. Of course, it's quite easy. You just randomly assign numbers to the different words, you remember them, and then you can reuse them. But on top of that, we would like to have that these words carry some semantic meaning. So words that are used in similar contexts should have similar vectors. For instance, here I made an example where I put different words, different adjectives, and I divided them in two dimensions. One dimension indicates whether it's a positive or a negative word, and the horizontal dimension whether it's about food or people. And then I can put the words in this scale and using the background knowledge, for instance, the lead thing that you usually do not say about people, but more often about food, and it's a positive word. Intelligent, I've never seen an intelligent banana. This is something you say about a fruit. About a person and not a fruit, good and bad, and these can be used for both people and food, and that's why they're in the middle. And so this is something we want to do something similar, but we do not want to have to hire a lot of people that do that for us and place everything in a multidimensional space. We actually want to learn it. So let's look at how embeddings are learned by artificial intelligence and by a machine. So a first step in this procedure is to turn the problem into a game. So what game? The game is guess the word. And what we're going to do, we're going to present the AI with a task. We're going to give some words, for instance, a sentence, and one of the words is blacked out. For instance, here, you all know this Florida man type of memes, which are usually based on true news articles, surprisingly enough. And so here, for instance, I have a title of a news story, Florida man charged for assault with a deadly weapon after throwing something into Wendy's drive-thru. I don't know if you know what it should be. I will tell you in the end. And so basically what we want to do is we want to train an AI in order to solve this kind of riddles and to guess the word. And why is this a nice problem? Because it's very easy to generate data. We can just take any text on the web, for instance, Google News articles, and the first word embedding systems were actually trained on those articles. We take some sentences, we take some context words. And so here I've reduced the problem. I'm not giving a complete text with one word masked, but I give two words before and two words after. And then the word in the middle is the one that I need to guess. And so Florida man charged for assault. And so the context words are Florida man and for assault. And then the solution is charged. man charged, assaulted with, and then the word is for, etc., etc. I think the principle is clear. And so we want to do exactly the same as we were doing with the chihuahuas and the muffins. We want to learn characteristics of the different words, of our context words, and based on these characteristics, we actually want to make the prediction of what should be in the position of the question mark. So in order to do that, the structure of the model is usually fixed, and it's fixed in such a way that when we learn the model, it will have some useful side properties. But for now, let's concentrate on the format of the model. So the input are the 4 context words that you see on the left-hand side, and the output here on the right-hand side is a probability distribution over all possible words. So here, if there are 5,000 words that are used in the news articles, this will be a 5,000 dimensional vector, where here the first position indicates the words sought, and there is a probability of 0.1 assigned by this model, blamed 0.1, and then the correct word charged gets a probability of 0.7. It all adds up to 1. And the structure of our model is, and that for each of the words, we will actually compute a vector, and this will be done by model 1. And then model 2 will just concatenate all these vectors and then learn a mathematical formula that turns these these numbers into probabilities. Why are we doing it in this way? And we're actually making the task a little bit more difficult for the AI, because the AI is actually forced to first make an abstraction of the words. And the way it makes the abstraction needs to be the same for every one of these words, and it needs to be consistent. The next time that someone is using Florida, the same numbers need to come out. But the AI will learn this model and will learn then based on these numbers in order to make these predictions. And because we have the combination of these two models, it's actually turned into an optimization problem where we want to optimize here an expected value. Let me explain this. And so basically we are going to look at, we have a lot of examples. So here for the input Florida man for assault, the correct answer is charged. So we will have a function that will express that this output that is given here by our model, how good it is for this particular problem. And that is what is called the loss function. That is what L stands for. So we have charged is the correct answer, and we will compute the loss of the prediction that we make with respect to the correct answer. So here, for instance, we could take a very simple loss function, just the difference. It should be charged, and we give a score of 0.7. So our loss is 0.3. What we want to do is we want to learn two models, model 1 and model 2, and such that in combination, the expected value of the loss that I have, if I feed my machine the data on which I train it, and that this loss is minimized. How do I want to minimize it? I want to learn good model 1 and model 2. And so my model 1 is expressed by my function f that is applied to each and every of the words, and it has parameters theta. And then I apply my function g that also has parameters omega, and that actually is then applied. And this is just an optimization problem, and we can use hill climbing in order to find, well, or gradient descent in this case, and because we're going down, in order to find a locally optimal solution. And that is basically what the machine does. It runs through the examples, and every time it makes an incorrect prediction, it will update the weights in such a way that it would improve the prediction for this particular example. So here we feed it with this example for the man for assault. This comes out, it's 0.7. So we're going to tinker a little bit with the weights of model 1 and model 2, such that this 0.7 maybe becomes 0.71. And this way we continue until we have a good model. So now we have made an AI that is very fun to play with, and because we can give it some words, it can do some kind of autocomplete, or maybe find some spell corrections if there is a misspelled word that is a correct word, by taking the context words and seeing if it has a high probability, the word that's in the middle. But that is not a task. Initially, what we wanted to do is we wanted to make this adapter. But if you have a look at it, that's actually what is happening here. We are only interested in a part of the model. So we are training the AI. It's like when we are training students. Sometimes we do some fun exercise, but okay, we want them to learn something, and here is the same. Here we want to learn the AI to learn a model that puts words and puts them into vectors. And by the way that our model was organized, it was forcing the machine to give numbers. Our first model should give numbers that actually make sense, that help it in order to predict the word that's in the middle of the 4 words. Because basically we give the 4 words, then it can only use these numbers that are given for the position of the word, and only these numbers can be used in order to predict what the word is in the middle. So what kind of properties do you want to remember of the word? Well, whether it's singular or plural. Why is that interesting? Because then you know whether the word in the middle is or are. You also want to remember whether it's a male or a female word, because then you will have to use he or she, and this might be interesting for the word in the middle. And this is also what is happening. So our machine actually does learn a lot of semantic information just by this mock-up task, and these are extremely useful techniques because now, and once we have learned this, we have done this task, we have trained it on our Google News articles, now we can use it in order to predict for tweets, whether it's a positive or negative tweet. Every word of the tweet, we run through it, and we get a vector. We take the average of the vectors, for instance, and then we draw the line, like with the chihuahuas and the muffins in this space. Of course, it's 4-dimensional, so it will be a hyperplane separating positive and negative examples, happy and sad tweets from one another. And well, this is basically what I said. This part of the model captures semantic information in a vector that allows it to play the guessing game, and we're going to use it for a lot of other applications as well. And capturing semantic information works extremely well for this task. So what you see here is, so words have been trained, and we have found embeddings in this particular way. This is done on Google News articles, and then it's actually, I think, 300-dimensional. It's being projected on the first 2 principal components, but that already gives an idea of how the position is of the words with respect to one another. So here you see, if you look at slow, slower, slowest, you take the difference in the vector in the positions of these words, and then these differences are very similar as to short, shorter, and shortest. So which means that there are dimensions that actually capture this this relationship between words, strong, stronger, strongest, and you can also use it in order to solve this kind of riddles. Slower is too slow, like shorter is too, and then you need to fill in the word that is missing there. You can just look at the position of slower and slow, what is the difference between them, and then add up this difference to shorter. Do vector arithmetic in order to compute a position, take the word that is closest to this position, and that will be short. The same with gender. The difference between men and women is almost the same as the difference between king and queen, almost the same as the difference between he and she, the difference between king and queen, prince and princess, etc., man, woman, sir, madam. So it captures a lot of semantic information. And this is extremely useful and has really, really nice applications. So here you see an application in sentiment analysis. So this is of tweets. You have tweets with a positive or a negative sentiment. Again, we compute the average position of the words in the tweet. The red tweets are the positive ones. The blue tweets are the negative ones. Again, a projection on the first 2 principal components. And you see that we can separate, or there are regions where red points are more prevalent and regions where blue points are more prevalent. If you also look at words that are mapped to those regions, and for the negative tweets, problems, crashed, crashing, issues, fails, they end up in positions that are close to one another. Things like better, best, congratulations, and they end up in another position. So for instance, there is a professor in this university that is using this type of techniques in order to detect cyberbullying. And so instead of having to make this kind of gazetteer methods where you have, okay, if it contains certain abusive words, then it's more likely to be an abusive text or related to bullying, and they can actually use these vector positions that carry semantic information in order to get a much better classification of the different tweets or the messages on social networks. So that's all really nice, powerful applications. However, it also captures cultural bias, and this should actually not surprise anyone because it's trained on texts, on news articles, and they're about society cultural bias will also be reflected because when we want to predict a word, well, it's interesting to know these cultural biases that are there in the text and for which you need to play the guessing game. So some researchers actually took this up and they were testing out. And so let's play this equivalence game. And man stands to woman like computer programmer stands to. And then actually if they do the vector arithmetic, so they take the difference between man and woman and they add it up to computer program, the word they end up and that is nearest to it is actually homemaker. Oof. That's actually not what we wanted. This is basically saying that a homemaker is a female version of a computer programmer. This is not correct. And this is a cultural bias because in similar contexts, when they're talking about a man, it's more often a computer programmer in these news articles. And when they're talking about a woman, it's more often a homemaker. Other of these equivalences that were found, sewing carpentry. Okay, that's logical. But also more harmful ones. And nurse surgeon. And so a nurse is seen as the female version of a surgeon. And so this can sometimes be problematic. You should be aware of it if you're applying this kind of techniques. Why is that? Suppose that this technique is used in order to create a tool for screening your CV and finding the perfect job for you. Well, we do not want to have this kind of gender stereotypes. We'll actually run into trouble. And then you can say, okay, will we run into trouble? It's just statistics. Nothing I can do about. This is basically how society thinks about these things. This is not my problem. Well, there actually has been a case. Let me immediately go here, where Amazon was using a tool trained by AI in order to do recruiting, and that tool showed to be biased against women. What you see here on the left-hand side, these are bars that indicate of the people that are working in these different technology-oriented companies, and whether they are male or female, and then the number of employees in technical roles. And there you see that on average in the technical roles, there are more males in the technical roles than females. The bar for Amazon is missing here because they didn't want to disclose these numbers, probably also related to this kind of issues that they were having. And so what they found out is that this mathematical model that was trained, which is very complex, looks like this cockpit of an airplane, so we cannot immediately see what is happening behind the scene. And that Amazon system actually thought itself that male candidates were preferable because, and that was what it saw in the data, it was actively penalizing resumes that included words like women's, like in Women's Chess Club captain, and downgrading graduates from 2 all-women's colleges. And this is basically something that we do not want because, okay, we're assuming that they're equally capable if they apply for the job, and that this is something historical, a bias that is historical, and that we definitely do not want to get into code and to get into our automated decision procedures in order to be perpetuated forever. So if you look at the word embeddings, I did myself a similar experiment, but now not with gender, but with ethnicity, and there you see something very similar. And because these texts, they also contain names of people, so I just took the most popular names, the most popular ethnic names, and I computed the distance between the positions, and then you see here different bars, and you see the similarity, the average similarity between a white female name, these are the blue bars, and the term robbery. And then if you look at the similarity, and so this is the inverse of the distance between robbery and the female name at 0.08. And if you look at black males, that's the yellow bar, and they are much closer to robbery than females. They're still not very close, a similarity of 0.16. Similarity ranges from 0 to 1, so it's not that it's like right that they are right on top of one another, but it's significant, the difference between the two. Everything that's related to criminality, criminal, gun, etc. We see what we expect, and knowing biases that exist. If you look at things like smart, intelligent, professional, these are typically words that are apparently associated more with males than with females, etc. And so this is kind of problematic, and you need to be at least aware of this, and depending on the application where you're going to use these things. A second example is COMPAS, and COMPAS stands for Correctional Offender Management Profiling for Alternative Sanctions. And this is a tool that was used in the United States to predict the risk of recidivisms. So these are people that are being convicted by the court of law, and they actually want to use this prediction of the risk of recidivism, recommitting a crime, in order to see whether they should be kept locked up or maybe can get an alternative sanction. And this was based on historical data, and it was actually a commercial company that trained the model, and the model was used in the court of law. Even judges were referring to it in their verdicts, and they were saying, okay, we are going to keep the person in jail, and because the COMPAS risk score is very high, and so they were actually using it as evidence. And one of the problems with this is a group of investigative journalists actually looked at the data, the scores that were given by COMPAS, because you have this, they need to be open about the verdicts. They are public, so they can actually look up and see what the risk scores were that were given. They can compare it to the demographic properties of the people, like gender and race. And they actually found out, and ProPublica, that's the name of this group of investigative journalists, that there was a big bias in the errors that were being made by this system. And so there are actually two types of errors that are important. Well, there are only two types of errors. Now, either you predict that this person will reoffend, or is at least at a high risk of reoffend, but the person didn't reoffend, or it's labeled by the system as a low risk, but they did reoffend. And so it got a too positive label, while it should have been given the negative label, well, negative for the convict. And if you look at the differences between white people and black people, then you see that the error where we predict that someone who is not reoffending is in a high risk class, that this error is way less often made for white people than for black people. And the other risk, and it's actually the other way around. And this was a system that was being used. After this was published, a lot of debate resulted, and actually they stopped using the system. But this company was actually defending itself, and the company was actually making a very strong defense. And I want actually to give this also to you, because many people that talk about this topic, they stop here. But I think that what follows is also quite important. So Northpoint, the name of the company that made the classifier, their defense was, well, actually we are fair, our scores are calibrated. And what do they mean by calibrated? That means that if you look at the different risk categories that they are giving, low, medium, high, that if you look at all the people that get into the group of high risk, and you look at how many of those really did recommit a crime, then for white and black people, these percentages are more or less the same. It's even slightly higher for the black people than for the white people, And so the light bar is the black people, and the dark bar is the white people. A little bit confusing, but that's the way this graph is. And here, there you see, and that there is at least not a very big difference between the two percentages. So if you're in the high risk category, well, it's not racist. It just means around 76% probability of recidivism, independent of your ethnicity. The same in the medium category, and then it's like 55. In the low category, it's still quite high. The system is not perfect, and there it's like 53%, let's say. But one thing that you can also see here in this graph, and that is what this black line is, that the black people are more represented in the high risk category than in the low risk category. And so the black line is just representing of all the people that are in this category, how many are black and which percentage is black. So actually in the high risk category group, 4 out of 5 are black, and in the low risk category it's 50-50. And that's of course due to all kinds of social differences between black and white population, like age distribution, etc., and that can explain why there are these differences. But okay, so this is North Point's defense, and I think it's a pretty strong defense. It means their classifier is fair. Then why do we get so many unfair outcomes? Well, that is basically if you look at the errors and where are the errors being made, and let's just divide it into a problem of two classes, and we are going to keep some people in jail, the one in high risk, and some people we're going to give an alternative sanction. So those are the people that are in the low and the medium risk category. Then if you look at where are the errors being made, it means that for the people for which we predict they should stay in jail, well, for almost 80% of them, it was the right decision because they would recommit a crime. But for 20%, it was a wrong decision. And this was a wrong decision, which is more negative for them than what they deserve. They would not recommit a crime, but they need to stay in jail anyway. For the people that are in the low and the medium risk group, it's the other way around. So the half of the people that are in the medium category, they get an alternative sanction and they deserve it because they do not recommit a crime. And so that is 100% minus where the bar is. But all those people that are contributing to these bars, well, for them it was a right decision. It was a wrong decision, sorry, to give them an alternative sanction because they will recommit a crime. But it's a different type of error than that we were making for those people here. It's a type of error that we're making here is we're giving someone a decision which is too positive because they will recommit a crime, and the same for the low risk category. There are no errors here that someone gets a label you should stay in jail while they are not recidivists, and because everyone here gets out of jail. And so that's what's depicted here. The red ones are the errors which are at a disadvantage, and all the errors that are at the disadvantage of the people are in the high risk category group, and all the ones which are at the advantage of the person, they are in the low and the medium risk group. And now, so where does the difference come from? Because black people are overrepresented in the groups that get this negative error, and white people are more present in the groups that get a more positive decision than what they deserve. And that is where the difference in errors come from. And so black is relatively more frequent in high than in low and medium. And that is also an explanation why we can be fair with respect to this calibration, but we're not fair towards the errors that are being made. The impact that there is of the decision that we based on our model is disproportionate for both groups. So this raises a very intriguing question. And what does it actually mean to be fair? Does it mean that we need to be calibrated, or does it mean that we need to be fair according to what ProPublica was giving? So a first attempt could be that we're saying, okay, we're fair if the decision is not based on ethnicity. In this particular case, ethnicity, in the case of the jobs, on gender, and the decision should not be based on ethnicity. However, if you do that, we get very quickly what we call the redlining effect. And the redlining effect means that this term comes from a practice that was used by banks when they were no longer allowed to give loans based on the ethnicity. They were actually dividing the map of the city into red and yellow and blue regions. And the red regions, they would not get a loan. And not very surprisingly, these were predominantly black populations living there. Something similar is happening here. If there is this correlation between ethnicity and the label that you want to predict, and there is a correlation between ethnicity and the place where people are living, maybe the age of people and differences in the distribution of ages, the jobs they are doing, whether there's a history of violence in the family. If there are some correlations there, and the classifier will pick up these correlations and will still indirectly discriminate on ethnicity. We've done a lot of experiments in this respect, and you really see it. Removing a sensitive attribute from your dataset solves almost nothing, and there still will be the same table. ProPublica will publish almost the same table there. So that doesn't work. So let's try a second attempt, and because North Point, what they were saying actually makes sense. It needs to be calibrated. If a classifier is not calibrated, that's a very bad thing, because there is something like a black high risk and a white high risk if they have different percentages. If you're high risk, it depends whether you're black or white, and we need to know that in order to interpret it. Is it 80% or 70%? So we do not want that. So we want to have calibration, but at the same time, we also want ProPublica's definitions, because, okay, we do not want our decisions to have different, a disparate impact on the populations where errors are unequally distributed. So let's summarize what we want to satisfy, and these are really like key slides. I really want to convince you that each and every of these conditions is important. So what ProPublica is saying, if you deserve to stay in prison, it shouldn't matter whether you're black or white. So that the probability of getting the high risk score, given that you're a reoffender, and that there should not be a factor, ethnicity, that plays a role in this probability of getting this label. And that clearly makes sense, right? On the other hand, the other error, if you deserve to be released, it shouldn't matter whether you're black or white. So the probability of getting the low risk category, if you're not a reoffender, it should also be equally high between black and white. And this can then mathematically be translated. I just put it here. It's not important that you exactly understand what the formulas are, but basically we want to learn a label y hat, which is close to the label y that we want to predict, such that the probability that you get the y hat equal to 1 and the high risk score, given that you are a reoffender, does not depend on A is our sensitive attribute, the ethnicity. And the same for if your true label is 0, whether you get an alternative punishment or not, should not depend on your ethnicity. The North Point calibration basically means that the probability that you're a reoffender, if you're in the high risk category, and the probability that you're a reoffender, given that you're in the low category, and this should not depend on your gender. And so that was basically what I was saying. There is not such thing as a high black risk and a high white risk. If you're high risk, it means 70% probability of reoffending, period. It's not like if you're black and you're high risk, it's 80%. If you're white and high risk, it's 90%. No, it should be the same for both of them. Again, mathematically, we can translate it. So the probability that your true label is 1, given that the label that was assigned to you is 1, and should be the same independent of A equal to 0 or A equal to 1. Damn it, it should have been A equal to 1 here. Whether you're white or black, it should be the same. So each of these conditions, they can be translated mathematically in this formula, and then we can just solve it. And we have 4 equalities. We can assign our label y hat, and we try to assign it in such a way, and we basically get a number of linear equations. And based on these linear equations, and this is really the bad news, and this will also not work, it can be proven that both together can only be realized in very exceptional conditions. And these exceptional conditions are as follows. Either there is perfect predictability. So based on the history of violence in your family, your gender, your age, for what crime you were convicted, etc., we can perfectly predict whether you reoffend or not. Well, and this is a picture from the movie Minority Report. Then we can as well do something like what is done there, that we can lock up criminals before they commit the crime, because we know on beforehand we can see in the future, we have a crystal ball, and not very realistic that this happens. Or the other case is if the recidivism rate is exactly the same in both communities. And so basically, if you cannot distinguish both communities with respect to recidivism rate, then you can also do that. But when you do not have this equal base rate, if there is a difference in criminality between the black and the white population, and I'm absolutely not claiming a causal relationship, and what I'm saying is a correlation because of social circumstances, if that is the case, unless we have the perfect classifier, we will always have to trade in one against the other. If you want to have calibration, we will not have the equal odds, and that was the other condition, the ProPublica condition. If we have the ProPublica condition, we cannot have the calibration. So here in conclusion, and that is basically the conclusion that I want to give in my talk, if you look at these problems, there is no universal definition of fairness, unfortunately. It's situation dependent, and you should actually it's also a policy decision that you need to make. It's not just about learning the most fair classifier, but also about what kind of errors are we going to allow or disallow. Exactly the same if I want to make something to predict whether someone will get cancer or will not get cancer. I will also have to decide when I train my model, what is the margin of error that I want to have? How bad is it to miss someone who will get cancer and predict that this person will not does not have cancer and not give him the right treatment, versus predicting for everyone that they have cancer, then I don't miss anyone, but then I'm also not very selective. A similar situation holds here with fairness. It's unavoidable that we will make errors, and it will be a policy decision on what error that you want to make. So once you have decided what kind of error you want to make, there do exist a lot of algorithms to learn classifiers and to balance them. And so if you learn a classifier by optimizing the accuracy and by doing this minimization problem with the muffins and the chihuahuas and learn the best line that makes the most correct prediction, and there exist techniques to actually make it also fair at the same time. And that depends on where in the process do they act. Do I want to clean it away from the input data, adapt the learning procedure, and so not learn the line that best predict, but also has a trade-off on fairness, or do I first learn the model and then correct the model? I will skip over these, and this is just an example of what is the price of fairness. And so if we want to be fair, we may actually lose some of the accuracy, and that is what is depicted here in the experiment. If you want to know more about it, then you should ask a question about it. But it shows that, and depending on how strict you want to be on the fairness, I may actually end up with something with which you will make a little bit less gains. But on the other hand, you may save yourself from some lawsuits. So to summarize, and this is the message that I want to get across to you, machine learning models are not fair out of the box. If bias data goes in, bias data comes out. That we saw with the embeddings. News articles have cultural bias, so the embeddings will also contain this bias. And the research about fairness is about how to build models that are optimal or that optimally avoid certain types of bias. And it's very important to know that the type of bias is partially inherent to decision making. You cannot avoid bias in all possible ways. Unequal base rates between groups will probably lead to differences in treatment. Voila, that's it. I open the floor for questions.
All right, thank you very much. So if you have any questions, type them in chat, and I will ask them to Tom. It may take a while to type them, but we'll wait. All right, first question. Do you think that it's a good idea to use a machine learning model for these types of sensitive applications at all? So if instead we use a human to make the same decision, do you think this decision would be more fair or less fair, given that the model is adjusted for some form of fairness? And perhaps the ideal solution is for a model to give advice to a human expert, but that the decision will eventually be made by a human.
Yeah, that's a very insightful, very good question, actually. So if you look back at the result that I gave, then this result does not depend on whether or not the classification was made by a human or by a machine. So this also holds for a human. Unless the human gives a perfect prediction every time, there will be either a bias in the errors that he is making, or there will be a bias, or the decisions will not be calibrated. So he or she will assign a risk that is too high or too low, depending on the ethnicity or gender of a person. So that's one part of the answer. I think it's very important that humans are always involved in the decision. And there are actually some safeguards there in the GDPR and the General Data Protection Regulation of the European Union that requires that every decision that is taken that has a impact on a person's life, that this decision needs to be verified by a human. So that is also a safeguard, and that's already pointing into that direction. Then I think that it is still a good idea to use algorithms in these contexts in order to support the human that has to take the decision. And the reason is also exactly this. And the better your predictions are, the less worse your trade-off between the different types of fairness will become. So if you can train a machine and the machine makes more accurate decisions, then based on these more accurate decisions, you may get a better trade-off between fairness and unfairness. And then the last aspect for this question, I think it's also important to include a human in the equation in order to avoid and that you get this very systematic error in some areas. A model can be very inflexible, while a human can still make the decision or can change his or her opinion based on lots of examples or lots of decisions that they need to make. And then they will at least not consistently always disadvantage people that have a certain number of characteristics. Yeah, but I like the question a lot. I think it was a very good question.
All right. Next question is from Kevin. How can we prevent people from treating machine learning systems as a black box, not understanding what happens, and maybe not even be aware of any biases introduced?
Yes, also a very good question. And now I will have to say that for every question. But anyway, it's true. Some machine learning models are black boxes, and nothing we can do about it. So it's not like people treating them as black boxes or not treating them. They are black boxes. So why are we using them? And that's because some of these black boxes just perform better than models that are interpretable. And there are decision tree models that just have a set of rules. If A is larger than 5 and B is smaller than 3, then it's in the positive class, and those we can very easily inspect and we can see why a certain decision was reached. If you look at deep neural networks, what Steven also will be talking about, and there it's often just very hard to interpret. We can see the mathematical steps that have been taken in order to reach the decision, but we cannot interpret them. So in order to remedy this situation, now also people are doing a lot of research on explainability of black box models. And one technique that there is very often used are counterfactual explanations. And a counterfactual explanation is an explanation where you explain the decision that has been taken for an instance, a person, by telling what are the minimal changes that should be made to the profile of this person in order to change the label that is given by the system. And so in this way, we can explain to a certain extent why the decision was taken. For instance, for a loan, someone is asking for a loan, then we can say, okay, the machine predicts that you should not be given the loan, but the decision would change if your salary would be 200 euros in a month higher and the loan that you're asking for is $10,000 less, or 10,000 euros less, to keep it in the same currency. So there are some efforts there. Yeah.
All right. Next question from Space Time Ninja. One of the ideal conditions was equal base rates. Has it been tried to truncate real-life data such that the condition is met, and if so, was there still a racial or other bias in the end?
Yes, and that's indeed a way to solve it, to divide your space into regions, in profiles, such that the base rates for all sensitive groups are equal in the groups. And that's definitely a solution, but then you should be able to define these profiles based on attributes that we call explainable attributes. Let's say, for instance, if it's about getting a loan or not getting the loan, the sensitive attribute is the gender of a person. And there we see unequal base rates, and maybe females are less likely to repay a loan than males, let's say. Maybe we could get into a fair situation if we divide by the income of the people. Maybe this decision is based on the income. If we divide it into a profile of people with high income, then the percentage of males and females become equal. And if you look at the ones with low income, they may become equal. Then I would say it's acceptable, because the attribute on which we first create these profiles are explainable attributes. They are a genuine occupational requirement, as it is stated in law. And they are important conditions, and there is an immediate causal relationship between the attribute and the outcome that we want to predict. So that's a good situation. However, if we then define the profiles in a different way, for instance, I don't know, the school that they went to, and some of the profiles are only containing females because it's an all-female school, and there's an all-boys school, well, and then we also get these equal base rates, but there it would not be acceptable. So I would say yes, it is a possible solution if you have an explainable attribute that allows you to divide it into such strata, and then you can play this game. And in research, approaches like that have been tried out, but are not always possible.
Okay.
It's actually one of my papers that is doing such a thing.
Right. Okay, two more questions. Mateo's question. So fairness can reduce to correctness of the model. Will we always prefer fairness over correctness?
No, there is a subtle interplay between the two. You have the accuracy of the models, or the correctness of the models is usually computed with respect to training data that is given to you. And in the situations where we require fairness, these are situations where we often assume that the training data that we have contains some bias. For instance, when we have the CVs and whether we should hire someone or not, and based on historical decisions, in the past they hired a person like this, so in the future we should also hire a person that has similar characteristics. There is the implicit assumption that this hiring decision was tainted by discrimination, and because of that, requiring fairness will increase also accuracy, but on the true underlying ground distribution. And that is why they seem to be in conflict one with the other, because we're measuring the accuracy with respect to data in which we presume that there are inaccuracies. But if we add to the data where we think, okay, there might be some biases in the data, in the labels that are in the data, so it's actually very hard to estimate the correct accuracy of my classifier on the true unbiased labels. But I have additional this assumption, and this assumption is that males and females are equally smart. If I have a fair model, it's more likely to be more accurate on the true unbiased label.
All right. The last question from Benjamin. What do you think about using algorithms that generate justifications for model predictions? Can these be used to remove bias from the model?
They can be used to remove bias from the model, and they can be a very helpful tool for the people designing the algorithms. So if they, in the testing phase, they design an algorithm, the algorithm makes predictions, they see an imbalance between, let's say, black and white people, then they can use the explanations that are given for the decisions in order to see whether something is going on that is not right, and that should be corrected. If they see that a lot of characteristics are being used that are not relevant for the prediction that is going to be made, they can correct for it and maybe remove some of the attributes from the data set or explicitly require the fairness. Let's say we have a system that decides whether or not someone should be checked in the airport. It should have an extra security check for terrorism. And so it is being predicted, and we see that for Muslims, it's much more often predicted that they should be checked. Then we can ask for an explanation. Well, if the explanation then is, okay, the tickets for this person has been paid for by a credit card that is not in the name of this person, well, this could be thought, okay, this is probably a good reason. But if the reason that is given is, okay, the person ordered a halal dish in the airplane, and then we can see, and then these explanations can actually help to make the models more fair. Yes, so I would say yes, it can help. And it also helps, of course, if you have been treated unrightfully, if you can ask for an explanation from the system, and then you can see whether it makes sense or not.
Okay, thanks, Tom, for the clear explanation, and thanks all of you for asking the questions. Now we'll take a short break, let's say till 9:10, and then we continue with the lecture from Stephen. Right? Hey. Hello again, everyone. It's time for the second and last lecture of tonight by Steven Latré. Steven graduated at the University of Ghent in computer science software engineering. He also did his PhD there and continued as a postdoctoral researcher. After a few years, he joined IMEC, where he recently became director. And on top of that, Steven also came to the University of Antwerp. He's now a full-time professor here. Today, he will tell us about deploying a neural network on a low-power device. And again, if you have any questions, keep them till the end, where you can type them in the chat. So let's begin. Let's hear from Steven now.
So indeed, my name is Steven Latré. I'm leading the ID Lab research group. We're one of the research group in the computer science department. We're actually part of two different faculties, and to make it even more complex, we're also not only part of the University of Antwerp, but we're also part of the IMEC Research Institute, which has scattered locations across Flanders. And so today I'm going to talk about tiny machine learning, and as Thomas already explained really well, it's deploying machine learning on a low power device. But before that, I'll give you a little bit of very short introduction to why this is really important before I dive into the more technical details. The fact that you're all here at 9:15 or 9:10 p.m. And are still interested in machine learning, even without alcohol, it really means that artificial intelligence is quite important right now. And I think it's also for us in terms of research is really the case. We're seeing that artificial intelligence conferences really sell out faster than Tomorrowland. So for example, 2 years ago, NIPS, one of the biggest machine learning conferences, sold out in under 12 minutes, thousands of tickets in under 12 minutes. So it's harder to get into a machine learning conference right now as it is than to get into Tomorrowland. And this was actually not always the case. Some of you might notice that AI actually has had its winters and its popular popular periods as well. Right now, we're definitely in that search of where everybody is super happy about what machine learning can bring, and that's because deep learning started as one of the big advantages. I personally started my PhD in, I think, 2006, and that was before the age of deep learning. And I still remember that I went to conferences where people really told me, why on earth are you doing artificial intelligence? You know that thing will never work, right? And now it's the other way around. Often people are asking yourself, yeah, why aren't you using artificial intelligence for that? And it's true, if you look at it, we've come a long way. So this is a small video I'm going to show you from 2004, the DARPA Grand Challenge. What was the DARPA Grand Challenge about, for those of you who do not know it? It was an international competition asking universities to build an autonomous car. And they gave the university a small track of about 200 kilometers in total in the middle of the desert, I think in Nevada or Utah, one of the two. And they said, build a car which is able to drive safely in the desert without that many obstacles. And what you can see is actually this was the result in 2004 of how this competition ended up. You can find really a lot of funny videos of how a lot of cars in 2004 crashed. And this was using artificial intelligence, and so the technology was definitely not ready yet. If you now fast forward a few years later, well, actually 2-3 years later, there was a specific university, Stanford University, that won this competition. They later on sold their technology to Google, and autonomous cars now look like this. We have millions of kilometers that have been driven already by autonomous cars, only in, let's say, a time frame of about 15 to 16 years. I think deep learning is is providing a lot of breakthroughs in a lot of other applications as well. About 15, 16 years ago, some of the main challenges that we were looking for was, can we recognize handwritten digits? Right now, we're in the area of deep fakes, where we can generate things from where we can generate any type of video sequence you want. This is one of the most cool breakthroughs I find myself to be in deep learning, where they're able to, based on a single picture, change the video sequence of someone. So I'll show you an example of this. Based on a single picture of someone, they're able to use deep learning to say, okay, we'll let that person dance, for example, in the exact way you want. So that's where deep learning is at this moment in time. And I could give a presentation today of about more than an hour about all the cool things that deep learning has given us in terms of innovation. But that's not what I wanted to do. So I want to focus a bit on, well, first of all, the underlying reason. Why is deep learning so unbelievably popular right now? So why does it result in those really breakthrough type of applications that we have seen in the last 10 years? Because in the last 10 years, we've really seen, whether it's more natural language processing, computer vision, and other cases that Ton also explained, we've seen a lot of breakthrough applications for deep learning. So the natural question is then, okay, it means that we will have breakthrough technology as well, because 10 years ago it wasn't possible. Now it's unbelievable. It's definitely possible, and people call this deep learning. So deep learning is to some extent a breakthrough technology. Well, yes and no. Yes, in the sense that it provides a new set of applications, but actually no, in the sense that all these different innovations or all these different technologies like artificial neural networks, which Ton already explained briefly as well, these already existed 10, 15, 20 years as well. And that's very important to know, that fundamentally nothing has changed. Yes, these things have evolved, but in the end, the same type of technologies are already or did already exist 20 years, 25 years ago as well. So you then might ask yourself, why does it work right now? Well, there are really good reasons why it works right now, and it actually has nothing to do with new fundamental technologies. It has everything to do with the way the computer landscape evolved. So you all know the Moore's law, I assume. This, I think, is Computer Science 101. You probably see this in week 1 or 2 of your Bachelor 1 in Computer Science. So Moore's law is saying that the capacity of our CPUs or computational units are becoming more and more cheap and faster over the years, following an exponential curve. Well, that Moore's law, that exponential increase in compute power, has resulted in a lot of advantages for deep learning. Things that were not possible 20 years ago are suddenly now unbelievably easy to do. When I was still a PhD student, I knew that when I needed to train a neural network, it took me about 6-7 days to train something really complex. It was complex for me. Now you would do this in 10 minutes without any problem. So that's one reason why deep learning has become so popular. There's a second reason, is that suddenly we have all this amount of data available as well. So artificial neural networks, deep learning, they thrive by data. If they don't have any data, and if they don't have an abundance of data, you will never be able to train a neural network. Now, other technology breakthroughs like the internets, Internet of Things, have resulted in a lot of important data searches as well, and as a result, also a lot of data that has been stored or is being processed right now as well. And the third thing is the exponential decrease in storage cost as well. It's one thing to generate all this data, but it's another thing to make sure that this data can be stored. And so these three evolutions together is actually what makes AI possible, and that's actually the reason why we're all talking so passionately, or at least I'm talking so passionately, and you're listening, I hope, passionately as well, towards why machine learning, why artificial intelligence is so important. So on one hand, we have faster chips. On the other hand, we have cheaper storage, and on the third, we have more data. And so fundamentally, and that's really important to know, machine learning, neural networks, they aren't really that different than what they were 15, 20 years ago. But they, of course, result in a lot of very important applications now. So what is the problem then? Well, there is a big problem that we're seeing. Yes, they're resulting in huge amounts of new applications, but we're also seeing that we're reaching a barrier. And today I'm going to focus on the barrier from a computational perspective. There are other barriers as well. There are ethical barriers where Toon focused on a bit today. There are barriers in terms of what can it actually do in terms of reasoning. It's also a very important barrier. But the barrier I'm going to focus on today is how complex are these things right now. And the evolution that we're seeing is that they're becoming really, really super complex. So what you're seeing is that every year a neural network is actually being generated, or the neural networks that are being generated are becoming more and more complex. You actually see that about every 2 years, the complexity of a neural network model almost doubles. So yes, every 2 years, or every few months, or every day actually, there are new neural network models and neural network architectures that are being proposed by researchers, always with much bigger capabilities. But the complexity, so the size of these networks, also is really becoming really huge. And you see that in this figure a little bit. This shows you the typical curve of type of accuracy that we got over the years on computer vision type of neural networks. So starting with AlexNet, which was one of the first deep learning computer vision neural networks, and then gradually moving to things like ResNet and Inception, which are ResNet at least very good computer vision classification algorithms. They're able to get really high accuracy, but the complexity of these things is also really, really, really high. And a very nice example of that is the GPT-3 algorithm that you might know. So the GPT-3 algorithm is one of OpenAI's neural network models. It's something that Elon Musk initially called too dangerous to ever release on human mankind, and then I think a month later he just released it on human mankind. But in essence, it's just nothing more than a really good autocompleter. So you can give it a few words, and then automatically GPT-3 will write an article for you. It was very recently, 2 weeks ago, the Standard actually published such an article by just giving it the first paragraph. So it's an unbelievably powerful neural network, but the footprint in terms of power consumption, and as a result as well in terms of carbon footprint for training that GPT-3 thing is unbelievably high. So it's actually equivalent to, in terms of training at least, to taking a car, driving that car to the moon and back. Well, the amount of emissions, so the carbon footprint that you're generating with just taking a car, driving to the moon and back, is so in the total 700,000 kilometers, is actually exactly or all more or less the footprint that you would that they needed to have for training GPT-3. And that's really a problem, and that is going to be a problem in the future as well. And that's a problem from an ecological point of view, of course, because these things are becoming more and more complex every 2 years. They're doubling, and we will not be able to keep on with that scale just from an ecological point of view. But it's also a problem from an application point of view, and that's because we have a separate trend as well in the last few years, which is called the Internet of Things. And that trend is going towards more and more distribution as well. So if you look at how the internet is evolving, we're seeing that we're getting an exponential increase in the number of devices that we connect to the internet as well. So think of smart light bulbs, smart thermostats, I recently bought a smart bird feeder, so you can really have any type of application that you want. You can link it to the internet. No, so that's really an exponential increase in devices. The expectation is that we're already at about 40 to 50 billion devices connected to the internet. And in a lot of these cases, all these devices will generate data. And as they generate data, they at least pretend to be smart devices. They have the potential to also have a very strong link with artificial intelligence as well. So it means that in a future world, and a world that is actually already quite near right now, is that if you look around in, for example, in a city, if you look around in your home, if you look around at your workplace, you'll have an environment where often tens to hundreds of devices are all there, often Internet of Things enabled devices. And these devices will produce some data that you often want to deploy, or that you often want to deploy artificial intelligence systems as well. So one thing you could say is, well, let's build a 6G or 7G network because these devices are going to generate a lot of data, and let's just pump all that data over to the cloud, do some artificial intelligence there, and we're done with it. Well, for a lot of different applications, that will simply not be possible. We see that the wireless communication link is often the bottleneck for a number of reasons, and for other applications, there are also other reasons why we wouldn't do it. I'll explain that in a few seconds. But just to give you an idea, if you would do that, for example, for an autonomous car, if you look at how a self-driving car, what type of data it would generate if you would push everything to the cloud, well, on that self-driving car, there are things like cameras, radar, sonar, GPS, LiDAR, which all produce streams of data in the order of megabytes to kilobytes per second. And that actually means about 4 terabytes per day of data for each autonomous vehicle that you have. If you would need to pump all of that over a wireless network to a cloud data center, where you then run some kind of complex AI model, that's never going to fly. So I think that's clear that we need to push intelligence to the edge. That's the only solution we have. We need to deploy our machine learning models to that autonomous car. We need to push that maybe to our smart bird feeder or to whatever we want. And so there's a clear technical reason for that, but there are also other reasons for doing that. So, for example, one technical reason is the portability of it as well. So there are already a lot of cases where, for example, new earbuds are coming up with AI-enabled systems embedded within, and you cannot just send all the data then to to a centralized location simply because you cannot have the right internet connectivity, or you cannot rely on the internet connectivity every time. But there could also be a non-technical reason for that, and that non-technical reason is maybe privacy-sensitive applications. So if you, for example, are building a smart camera, well, that smart camera will record a lot of data. Well, do you want that smart camera to actually send all the recordings it makes, which is happening right now actually, to a centralized cloud data center where it will be stored and might be processed by other people as well? Well, often in a lot of cases, you don't want to do that. Same thing with brain-computer interfaces. Elon Musk is developing with his Neuralink company, is developing a chip that links with your brain. whether it will ever fly, that's a big question, but at least there are other organizations working on that as well. Again, the data that interfaces with your brain, do you just simply want to offload that to the cloud? Well, some might want to do that, others will definitely not want to do that. So this privacy sensitivity is a second reason why we really want to have machine learning on the devices as well. And you might think, well, that's pretty futuristic. Brain-computer interfaces. When will we ever have this? Well, that's true, but there are already a lot of applications right now which really require that. And this is just a bit outside of the talk of today, but just to give you an example of that, this is something we developed together with the company RoboVision, where we actually built a smart camera for COVID tracing. So this is an example of our deployment at the Mer. What we did is we put a camera at the Mer. We tracked we recorded for 6 months this the people on the Mer, and we tried to check with very standard, simple deep learning systems. Are we actually able to measure how close people are walking? So are they walking within a 1.5 meter distance or not? And then we could give some guidelines to the city of Antwerp, how much those safety regulations were abided to, yes or no. We did this, and we did this actually as a showcase also to show that we need more privacy-sensitive applications as well, because in the end we pumped all this data over to a centralized cloud and did the machine learning in the cloud, but everybody felt really uncomfortable with that situation. It was okay for a research experiment, but if you would really want to track people for a longer time, there was really a request from the government or from the city as well to make sure that actually the smart camera would never output any video data, but that it would only output statistics about what it records. And I think a lot of these applications really require this. So this is just to give you a bit of information that, yeah, smart that machine learning to the edge of the network is often from a technological perspective important, but also from a non-technological perspective important. Okay, so given that, how do we do that now? Well, it's not that easy, to be honest. And it's not that easy because the current hardware that we have available is actually pretty limited. On this figure, you can see the type of hardware that we have available to run machine learning systems on. So these are typically GPUs, sometimes it's a TPU or a CPU, or in more embedded sphere, you have things like ASIC and so on. And so what you see is that what you see here on the x-axis is the power consumption that these things consume, so these devices consume on a logarithmic scale. And on the y-axis, you see how much operations per second that they can tolerate in all of that. And that means that on the diagonal axis, you actually get an indication of how many operations it can produce per amount of watts. And what you see is that almost all devices are really on the right-hand side of this. So this means that the main category of devices that we have right now are often very complex in the number of operations that they support, but they're also very power hungry. So the Tesla V100, for example, really good GPU device. If you would want to put something like that in an Internet of Things sensor, it will probably take you about 5 seconds before your battery runs out. So definitely not possible. And so if you look at the type of markets that we're going towards in the future, Internet of Things, mobile, automotive, they actually require a lot less power consumption. So those 3 vertical axes you see here, that's the domain that we want to go to in the future. With automotive, there's still quite a bit that you can do. But the moment you're going to mobile phone devices or you're going to Internet of Things devices, the type of machine learning that you can run on a smartphone and especially on a sensor device is almost impossible. That's also the reason that if you ask that digital assistant of Apple, I'm not going to mention her name, otherwise my smartphone will run off, but if you mention a digital assistant of Apple, that only the, hey, you know what I mean, is being detected on the device. All the rest, the question that you're asking later on, is it being sent to the data center to build on a machine learning system, to run on a machine learning system there. And in the Internet of Things sphere, where maybe you want to do some air quality sensor neural network type of thing, it's even more impossible to do this. So one thing that is really being developed right now, as we speak, also not by me, but by colleagues from me at INEC, is new type of hardware which is able to run at much less power consumption and still tolerate sometimes of some type of operations as well. But while the hardware is being developed, it's important that the software follows the same path as well. So it's important that we build new type of software algorithms where 99.999% accuracy in terms of the neural network is not that usually important. Well, it is still important, but the prime importance is actually building machine learning systems that are much smaller in terms of computational footprint. And that's exactly what part of my team is doing. And we have two approaches for that. And I think actually one of my PhD students is focusing on the left approach, and he's actually here today if I saw one of the questions. But we have two approaches for that. One approach is making current deep neural networks smaller. So you have a certain machine learning system already. Can we, in some extent, make that machine learning system just smaller so that it still does what it needs to do, more or less, maybe a little bit less accurate, but that it at least has a much lower power consumption in terms of the number of operations that it needs to do and the memory footprint as well. So that's one direction that we're focusing on. The second direction that we're focusing on is can we build a completely new type of neural network, which is very strongly interacting with the hardware as well. So can we build a hardware and software co-design of systems where we build a neural network which immediately is optimized for a specific type of hardware, and as a result also runs at a power budget that is 1,000 times less than current GPUs. So I'm going to explain in those two approaches in a bit more detail of what we do in that sphere. So the first thing that we do is we try to make existing deep neural networks smaller. So if you look at a standard deep learning image classification system, it really depends on the type of task, but I think you should, I think rough ballpark figures is that a normal deep learning image classification system nowadays requires about 1 gigabyte of memory and about 1.2 watts of power consumption. These are really huge numbers, especially if you want to deploy this into Internet of Things devices. So already for a smartphone, you need about a 5 times reduction in these parameters. If you're going to an Internet of Things device, you need about a 50 times reduction of these parameters to actually get something going. So what we try to do is we try to start with these standard deep learning neural networks, which Tom already explained, I think, very briefly how a neural network looks like. And we're trying to make this less complex. And the way to make this less complex is a process called compression or pruning. Or pruning is a form of compression. What we're actually doing is we're trying to remove connections between the neurons of the neural network, which are less relevant for us. So we're trying to remove those connections. We're even trying to remove some neurons. And we're trying to do that in an intelligent way, of course, to make sure that those neurons still give you a decent level of accuracy. Can we do that? Yes, we can definitely do that, because if you look at the typical type of neural networks, they actually have a huge number of parameters. So a huge number of neurons with very little weights, a lot of synapses as well. And often it means that it's that you can actually prune, so that you can actually remove a lot of those connections. So typical state of the art is doing that in a classical way. They're looking only at the weights and the connections in that sense, and they're just saying if the weight is really low, the neuron is not going to be important at all. So what we're going to do is we're going to remove part of this neural network so that it still does more or less the same, but only by removing a few lower weights and lower connections, and that's what they do then. This works quite okay, but really for Internet of Things devices, this not give you that 50-factor compression that you want. What we do in the group as well, we do it more based on a knowledge-based approach. It actually means that we look more at what type of application do we want to focus on at this moment in time, and we really look at, can we get some explainability from our neural network, and can we really understand what these neurons are doing, and we're trying to prune more as a result. So we're really going to the far edge of the furthest limit of what we can do, and we really prune a lot of these things, also often having a large impact on accuracy. So sometimes it means that we're saying, okay, these two outputs, for example, we do not want to make a distinction anymore between a pedestrian and a sign. Well, we're going to combine that. It's going to be with a loss of accuracy, but now it's really possible to deploy this on an Internet of Things device. I think the advantage that we have with that is that we can start off with a very general artificial neural network that is able to do a lot of detections, but then we can always prune it specifically to the application that you want, and that really has a big advantage. So one thing we do really in the group is that we try to make this as tangible as possible. So we don't only do this from a purely software perspective, but we also make sure that we really translate that to a hardware implementation as well. And so what you can see here is a robot that we have running around in our offices in Antwerp, which is able to do exactly that. So we start off with a really very big deep learning system, which has this 1 gigabyte of memory and 1.2 watts of power consumption, and then we really compressed it so that it really fits a very small embedded device on this particular robot. But it also actually resulted in a drop in what we can detect. So right now we can only detect like a banana and a bottle of beer. Pretty simple. It's more of a toy example, but it resulted in really an important power consumption reduction as well. Okay, so that's one thing we did, and with this compression of neural networks, you can go really a long way already. So this really gives you a very large impact. But in all honesty, it has its limits as well. If you start off with something big, you make it smaller, there's a limit to where you can make it smaller as well. So more fundamentally, we're looking at more complex type of neural networks, which we call, well, second generation or biologically inspired neural networks. So what is the motivation for that? If you look at the type of neural networks that we have right now, so the typical artificial neural networks that we have right now, they have the problem that I just discussed. You could do training in the cloud, but the moment you want to execute something, in the best case, you can actually run it already on the device. In a lot of cases, you still need to run it on the cloud as well. If you really want to go to more dynamic intelligence, systems that are able to learn and adapt themselves, you need to do some kind of pre-training in the cloud, and you need to have a system which is constantly learning on the device as well. And we believe that the current type of systems, including those compressed neural network systems, are not going to be able to really do this continuous learning on the device as well. So what are we doing in that case? We're actually throwing away what we know about artificial neural networks, or at least in the current design of those artificial neural networks. Because if you think about it, these artificial neural networks, these were originally deployed or mimicked after the human brain, but our human brain is much more power efficient than these neural networks. So our human brain only consumes a few watts, even less, I think, which is way more capable of doing stuff than a simple computer vision system, which uses a lot more watts and is much more complex. So if you really look at it from a biological perspective, there's something that we're doing wrong. And one thing that we're doing wrong is that we're actually making a very oversimplification of how a neural network, so a real neural network or brain, looks like. So how a typical artificial neural network looks like, and this is something that we already defined 20, 30 years ago, it's combining a bunch of real valued weights, so numbers, combining it with a certain sum, doing a certain activation function on it, and outputting something. But these are real valued numbers that we're using as input, and as output we're giving a real valued number as well. Our human brain works completely different. Our human brain works based on electrical impulses and not based on numbers. We're not a computer where we're constantly saying 4, 5, 3, 2, 1 to the different neurons. No, we're giving electrical impulses or spikes that encode information from one neuron to another. And apparently, for some reason, that works really well in our human brain. And so what we're looking at right now, and we're definitely not the only ones, is can we build new types of neural networks which are more closely linked to how our human brain is working? And more specifically, can we rely on that concept of spikes, so electrical impulses that go from one neuron to another, to ensure that maybe this is going better for some type of applications? Now, that's not something that we invented. This is something called spiking neural networks, and these are at least a family of one of what they often call the third generation artificial neural networks. So to just give you a little bit of history on one slide of neural networks, it started a very long time ago with the multilayer perceptron, where basically you only transferred information with zeros and ones between neurons. Artificial neural networks gave that a real value by saying, okay, neurons can now give a value between 0 and 1 as an output. In spiking neural networks, we're not using real values anymore. We're using spikes, so electrical impulses, or at least we're mimicking electrical impulses the same way we know that the neurons in our human brain do this. And we're trying to encode information in these spikes. So a lot of spikes together will probably generate a higher number, which will cause another neuron to spike as well. So this is really more fundamental research in the sense that these are completely new type of neural networks that we're trying to build. They do definitely not work in most of the cases as good as deep learning, but we're hoping that they will generate some new breakthroughs as well. So without going into much more detail of how this technically works, let me just give you an example of an application of something that we built with these type of spiking neural networks. Some of you might recognize this device. This is a Google Pixel 4, which had a very specific additional chip, this one here, which was a radar that they embedded in the Google Pixel 4, with the idea that you could make notes without really touching the screen, especially in COVID times. This is getting more and more popular, that you do not want to touch a touch screen anymore, but you just want to hover above it and give some specific gestures. Was released a few years ago with a lot of fuss, was an unbelievable disaster, actually, this Google Pixel 4, and specifically that radar chip, because it simply didn't work. And you can also see that the new Google Pixel 5 actually ditched that radar chip again, because it simply didn't work. And why didn't it work? it didn't work because the results, the accuracy of that Google device was just not good enough. So you were able to do about 11 gestures on that device, swiping left, swiping right, zooming in, zooming out, and so on. And Google used a traditional deep learning approach for that, convolutional neural network combined with an LSTM. And for that, they got actually the following results. If you just generalized across all the different users, they got a result of about 88%, which means that it still failed in 1 out of 10 times. If you did a per user training, so if you asked the user to record some gestures themselves, it would actually get a better accuracy of about 94%, but still not really doable. What we tried is using the same data set of Google. We tried to do this with spiking neural networks, because radar information is really something which also happens in spikes and in a temporal way. And that's perfect for spiking neural networks to interpret these more non-typical vision type of things or non-typical image type of things, but really more temporal inputs. We translated that to a spiking neural network combined with a liquid state machine. And then we were able to build a system which was able to do the same type of gesture recognition. We actually did this like a half year ago with the goal of building a much smaller system to really deploy it on a low power device. And we said, okay, let's try to build this on a low power device, and we will probably get some hit in terms of accuracy. To our own surprise, we actually got a much better accuracy than what Google had with its deep learning system. So it was really, for us, a reason to pop up a bottle of champagne, because we got we built a neural network system that was about 100 times smaller than Google's system, and even better, it had a 4 to 5% bump in accuracy as well, and 4 to 5% bump that really matters. If you make a personalized model where you build it for the specifically for a person, so you let the person record some of those gestures, you're really able to get a 99% accuracy. So it's really building a chip that works in that sense. I have a small video of how this actually works for a very simple case. So what you can see is really here, if it wants to work, it's a gesture of some of my colleagues here who are doing these gestures. So they're swiping left, swiping right. On the left-hand side, you can see the input and how the neural network works. But on the right-hand side, you can see how this is able to scroll without any touch through a collection of images. So now my colleague is zooming in on the picture by using his gesture like this as well, and he can zoom out as well. So this is coming a bit closer to Minority Report type of applications, or to Iron Man type of applications. We're definitely not there yet, but it's one step closer. I think one last thing to mention is that I really focused on the software side now, but hardware goes hand in hand with this. So if you really want to make this in a low power way, it's important to really have a very performing hardware chip as well. That's also one of the reasons why we're focusing on, and that we're also part of inequalities. So it's super cool to see that we can do this hardware software design together. inequalities also, together with us, they also released very recently the first spiking neural network based chip for radar processing, based on what we did there as well. So it really goes hand in hand, and I think that's where we can really make a difference. So to summarize, why is tiny machine learning or machine learning on low power devices important? Well, I think it's important for a number of reasons. If you think of the future and you ask a bunch of people, how will the future look like? Often they're talking about these self-driving cars, or we're going to have a chip in our brain, or we're going to have a smart city where everything is filled with AI, or we're going to work together with robots. Well, these are definitely applications which are in the making, but these are applications that all bridge AI and Internet of Things. And so it's super important that we build better low-power AI models in the future as well. And the only way we can do that is by doing hardware and software co-design together. If we really do this, we can build really complex models because of that. And something I didn't focus on today is I'm also very convinced personally that this could be a strategic asset for Europe. Because if you look at how the AI world is evolving, we're seeing those big players like Google, Facebook focusing a lot on those data center type of AI. I think for a large part, we lost that type of competition to Asia and to the US. But I think in the more low power type of sphere, Europe has some important players. I'm not saying this because I'm part of IMEC, but IMEC is a world leader in nanoelectronics, so they are doing a lot of stuff in that sense. Not my expertise, but other colleagues within IMEC. And there, I really think that we can win, or we can at least have a unique select position for Europe in the domain of AI as well. So to make a little bit of shameless advertising for what we're doing within the group, if you're interested in this and you want to make a difference in the artificial intelligence world, I really think that everything with low power, resource aware artificial intelligence could really make a difference in the world. And you're definitely interested to talk with us about doing a research project in that sense. Having said that, I think the number 2 strategic asset that Europe has is, for me, trustworthiness and fairness. So I definitely think that Ton is doing unbelievably good research in that sense as well. And I'm not only saying that because I know he's still watching this YouTube stream as well. But I think that's equally important for Europe, where Europe can make a difference as well. Thanks a lot. If there are any questions, I'm happy to answer them.
Right. Thank you, Steven. Let the questions come. So type them in the chat. All right. First question. Maybe Steven, I think, I don't know if it's me, but I hear a little bit of feedback, maybe.
Sorry, that could be my mobile phone, which was too close, so I hope.
All right. So the first question from Thomas. Can the chip created by IMEC run inference on arbitrary SNNs of a certain size, or is the build specific, or is it built specifically for the shown radar use case?
Yeah, it's a really good question, Thomas. Well, it's really specifically for that radar use case, and it's for 2 reasons. Reason number 1, spiking neural networks are really cool. I love them, but they're definitely not at the same performance of what a typical deep learning system can do. So don't use spiking neural networks at this moment in time for the things where deep learning actually shines in. So computer vision, natural language processing, spiking is not that good for that actually. So it really is really good at this moment in time, at least with the knowledge that we have, for what we call extemporal applications. So that can be spatial temporal or spectrum temporal applications. So applications where there's a lot of temporal, variations in time as well. So for video processing, It already has a better accuracy. For radar, which is by definition more temporal, it works much better. So that's one part of the answer, in the sense that you really need to do it for these type of applications, and it's also therefore integrated within the radar chip again. The second reason is that there are other companies like Intel. They are building their own chips as well, also spiking neural networks. Intel Luihi, for example, is a spiking neural network chip, but this does not focus on power consumption at all. So they really try to build chips for data centers again, and the type of neural networks that they support is way more bigger than what inequalities is doing. And in all honesty, that's purely a matter of cost. What Intel can do, that Intel Luihi chip, in terms of development, it costed billions of dollars. iMac does not have that money, unfortunately. So we're focusing really on that low power part again as well.
Okay. And a question from Spacetime Ninja. Maybe not really a low power question, only a question about low power device. But is there any progress in machine learning combined with quantum computation?
Yes and no. So it's definitely something that we're starting to look into. So quantum computation can indeed, more I think in the data center side, can potentially provide some breakthroughs into the parallelization of how you do search and how you do certain computations. So I think there is for sure a potential there. I wouldn't say that there is already any breakthrough in that combination, because I think it's very early days. So, for example, iMac is building its own quantum computer as well at this moment in time, and we're looking at that as well on the machine learning side. But what we do see is that we're really in the, I would say, very first type of machine learning tasks that we can crack there, far from doing any radar application or radar detection. That's, we're really in the very simple things like recognizing handwritten digits, for example. So the stuff you talked about, we looked at in deep learning about 20 years ago, is what we look at right now with quantum. Not because it's not going to be feasible, but at this moment in time, it's the two technologies combined are too immature.
Okay. Then another question from Thomas. In the shown example use case, you still use a traditional deep learning classifier at the end of the network. How is this handled by the chip?
Yes, really good question. Again, so what we did here is we didn't apply it yet on that chip for the gesture. So indeed, the last classifier is pretty straightforward. It's just a random forest. Random forest gave us the highest accuracy. We want to replace that in the end with a fully spiking system, but we're not able to do that right now, in all honesty. So what it typically does is the spiking chip does like 95% of everything you need, being the spike encodings and the liquid state machine. And then the last part, we hand it over to a standard ASIC. But because we're then able to do very simple random forest algorithms, not really a complex neural network, the power consumption is still way below what you typically would have with a deep learning system. But you need those two chips. You need an ASIC or some kind of CPU linked with that radar chip still.
Okay. Then a question from Stan. If learning would be done on the device itself, how would knowledge be shared between different devices?
Yeah, really good question. Well, it depends. So it depends really on the type of application. So there are applications where knowledge is still being transferred centrally to a system, for sure. And then you would have some system where every day, week, month, depending on the application. You centralize, in a centralized way, you train everything and you push it again to your device. And then your device only updates itself with more recent knowledge. That's one way of thinking of it. There's so that's really a client-server type of system, if you would think of it. You could have a more peer-to-peer approach where where knowledge is indeed shared from one system to the other. This could be simply by pushing data to the next device and that the device does it itself. But there's also a concept called federated learning. And in federated learning, you're not pushing the data from one side to the other, but you're pushing the model from one device to the other. So the idea is that if your application is privacy sensitive again, that it might be better to just train on a single device with privacy sensitive data and then push that model to another device where you train it again with your locally available privacy sensitive data, but that data is never shared between devices. And you can really go all the way with that. So there are really things that we're looking at as well on what we call swarms on a mission, where different types of machine learning devices try to constantly exchange knowledge between each other as well. So think of, for example, a bunch of robots who want to explore an area. It could be that you do this really in an online fashion, where one robot is seeing something and immediately signals this to another robot, which then is being used for its learning process as well. So you can go really, really complex with that. The most easy thing is, of course, just the client-server approach, but it's not the most flexible approach.
Mm-hmm. Okay, and then the last question from Thibaut. Do you think it would be better to specifically train networks for these lower power systems, or train them for high power system and then prune them to be runnable on low power systems?
I think it really depends on the type of application that you want to support. I think where we are right now, to really build generic systems, pruning is often the best approach that we have. And that's the approach that we're taking with the first sets, where we say, okay, we have a teacher network and we're having a student network which we compress. We see that gives us the most generalized results in the sense that you can simply apply this for every type of application you want to some extent. The second approach, we're already doing the training and the learning and the inference all on the same device, all on a low power device. So the spiking neural networks is more suited for that. Personally, but it's my personal judgment, I do believe a little bit more in the future potential of that approach. But I think at the same time, if you really want to have an application right now, those type of doing it immediately, training and learning all on the same device is not something that we're able to really to do in a good way. Because if you would do it in a standard deep learning way on a low power device, what you're actually doing is you're setting yourself back 20 years ago. So the reason why 20 years ago people said, well, deep learning and artificial networks, well, mainly artificial neural networks, they will never work. It's exactly that. It's because they were so slow that they could never train in a decent way. So if you're now going to say we're going to use that system immediately on a low power device, it will take you too much time to actually train something, and that's why I believe a lot in those and the potential, at least, of spiking neural networks.
Okay, another question just came in. You mentioned several times that current networks mostly use real valued numbers. Can it be interesting to use complex valued numbers instead in order to introduce effects such as interference? Yes, I believe it's a physicist who asked the question.
Well, yes, there are actually much more rich representations that you could do with all of this. I do believe it has been tried as well with varying results. I'm not an expert on the more let's say, making it more complex. I'm more an expert on making it more simple, so I can still comprehend it. But it's definitely something that people are looking into not even going to complex numbers. There's, for example, also concepts coined by Geoffrey Hinton, one of the inventors of deep learning, so the guy knows what he's talking about, on using vector information and also complex vector information. It's called capsule networks. And what we do see with all these approaches is that they fundamentally have often better capabilities of doing learning, but at the same time, they're becoming so complex in their computation that it's becoming even harder to train them and even harder to train them at a decent time. So it's a bit of a trade-off. How complex do you want to make that system? Because the more complex you make the system, the harder the training will be, and so the less data you can give it to it, and so it's not always that easy to find that good balance. And with the current artificial neural networks, with the current CPU systems that we have at our disposal, I think we reached kind of a good sweet spot, and that's the reason why deep learning is becoming so popular. So maybe in 10 years or even 5 years, those more complex representations would actually scale much better.
Okay, that was the last question. Thanks again, Steven and Tom, if you're still here, for the interesting lectures. And thanks for the audience to be here and to show interest and ask a lot of questions. And maybe we see you next time. So for the time being, bye, and thanks again, everyone.
Thanks, bye.